Welcome back. This is a new video offered to you by the Ceuster Academy. My name is Luc de Ceuster, founder of the Ceuster Academy, and in this YouTube video I will talk about the Chinese remainder theorem. Basically, it means how will we resolve a system of linear congruences. But before we start, do not forget to click the subscribe button if you didn't subscribe to my channel yet. Click the bell button so every time we have a new video, YouTube will inform you about that. But let's now have a look at the content of this video. We are going to look at a system of linear congruences. So x is congruent with b1 modulus m1, and we have theoretically n possible equations that we can consider here. Now, what does it mean? Well, it means that the value x, when divided by m1, has a remainder of b1. When it's divided by mi, it has the remainder bi, and when it's divided by mn, then it has a remainder bn. So we try to find the value of x which complies with all those equations. Now, we can prove that there is a solution, modulus m, and m, big M, is the product of all the moduli that we consider, and there is a solution when the GCD of all those moduli is equal to 1 when I and G are different. So the GCD of Mi and Mj is equal to 1 when the index is different. So I and J are not the same. Basically, this means that those moduli are relatively prime. They don't have to be prime numbers, but they have to be relatively prime. The Chinese remainder theorem is called the Chinese remainder theorem because this originated from a problem that was stated by Sun Tzu in the Chinese history, and we try to find a solution for that. So basically, we want to find that value of x for which it has the different remainders when divided by these different moduli. Now, when we look at the element, we also have to say that the bi, the coefficients, are integers. And of course, when we find this, when we have this system, we can prove that there is a solution when we have those conditions, when all those moduli are relatively prime, and that solution can be expressed as x is the sum for all the different equations from I to n, bi times mi times xi. And what we have, bi are the coefficients here, mi is in fact the modulus m divided by mi. And the thing that we have to do here is to identify the values of xi. And in the constructive proof, we can find the relation, how to find the xi. Those parameters xi can be found by multiplying mi with xi, and these have to be congruent 1 modulus mi. Basically, we have to find the inverse of mi modulus mi, and then we can find that value. So we multiply both sides, and this mi multiplied with the modular inverse modulus mi will be equal to 1, and here we will find the value of that inverse. So basically, finding those inverses of those different equations will give us the final solution. That final solution is in fact valid let's say, modulus m. So we will find x modulus m as a solution, and when x is larger than m, of course, we can find the remainder of this equation. And that's basically what we're going to do when we will be looking into resolving the system of linear congruences. We will do some exercises, and let's apply this first on the original Chinese remainder theorem that was defined by Sun Tzu. Let us now apply the Chinese remainder theorem on the original problem, how it was defined by Sun Tzu. First of all, what we say is that we have a number when divided by 3, its modulus is 2. When divided by 5, its modulus is 3. And divided by 7, its modulus is 2. And what is this number? When we look at the description of the text, it in fact represents this set of 3 linear congruences. And we're going to apply the principles that we determined before. Step 1 is in fact verifying if the moduli m1 equal 3, m2 equal 5, and m3 equal 7 are these relatively prime. So we have to verify that the GCD of mi, mj is 1 for I is not equal to j. Now when we look at all these 3 numbers, in this case it's very easy to verify because 3, 5 and 7 are special numbers, they're prime numbers. In that case we know that the GCD of 2 prime numbers is always equal to 1. So basically we can say after verifying step 1 that this set of linear congruences has one unique solution. Step 2 is in fact determining the modulus because it's a unique solution, modulus m. And modulus m is in this case m1 times m2 times m3, and when we multiply 3 with 5 and 7, we find that this is equal to 105. Step 3, now we have to define or find mi, which is m divided by mi. And we find for this m1 is 105 divided by 3, which is 35. m2 is 105 divided by 5, which is 21. And m3 is 105 divided by 7, which in this case is equal to 15. Based on this, we can write the equations how we find the terms xi. And that's step 4. We have to find mi, xi, which are congruent with 1 modulus mi. And mi and big mi and small mi are relatively prime because the way we define them. So the first one would be 35 times x1 is congruent with 1 modulus m1, 3. And we can in fact simplify this. We can say 35 modulus 3 is 3 times 11 plus 2. So basically we find here 2x1. Then we have, if for x2, m2 it's 21 times x2 is congruent with 1 modulus 5, and 21 is 4 times 5 plus 1. So basically we find here 1. And the last one, x3, is in fact, or m3 times x3 is 15 times x3, congruent with 1 modulus 7. And here we see also that we have 1 because 15 is 2 times 7 plus 1. So basically we can find immediately from this equation that x2 is equal to 1, x3 is equal to 1, and we find here 2x1 is congruent with 1 modulus 3. When we multiply both sides with 2, we find 4x1 is congruent with 2 modulus 3, and 4 modulus 3 is equal to 1. So we find x1 is equal to 2. So basically we found those parameters x1, x2 and x3. We have m1, m2 and m3. We have b1, b2 and b3. So basically now we can find the solution using the general formula, adding, let's say, m1, b1, x1 plus m2, b2, x2 plus m3, b3, x3. And that we will do when we clear this board. In the table you see the values we found before. The bi, b1 is 2, b2 is 3, and b3 is 2. We found that x1 is equal to 2, and x2 and x3 are equal to 1. From the calculations of the parameters mi, we found that big M1 is 35, big M2 is 21, and big M3 is 15. What we have to do now is to multiply these numbers, and that's why this table is very interesting, because we have 2 times 2 times 35, which is 140. When I take 3 times 1 times 21 is 63. And the last one, 2 times 15, is 30. And when we add all of them together, we find here 233. And of course, we have to add here modulus m, modulus 105. Now, we can write it here, so x is equal to 233 modulus 105, and we know that 233 is 2 times 105 plus 23, which means that x in this case is 23. And that's the final result, that's the solution of the Chinese remainder theorem here. 23, well, when we divide 23 by 3, the remainder is 2. When we divide 23 by 5, the remainder is 3. When we divide 23 by 7, the remainder is 2. And that's basically the solution for this this combination of linear congruences. That was the first part, the first video about the Chinese remainder theorem. We will do some other exercises in some other videos. Anyway, do not forget to watch or to read the text below the video. You will find some interesting links to our courses on our website, theceusteracademy.com. And of course, with every course you have a very interesting coupon, a coupon that will give you a very interesting discount when you subscribe to the course. It's the end of this YouTube video. Do not forget to subscribe if you didn't do it yet. Click the bell button so every time we have a new video, you will be informed. I'm looking forward to seeing you in our next videos. Thank you and bye-bye.